Hi everyone. Today we're going to continue our discussion on bonding hybridization from yesterday's lesson, where we took a look at how the valence bond theory was able to describe how two atoms come together in forming of covalent bonds. Today we're going to tackle the second problem, which helps to describe how chemical bonding occurs when they have multiple bonds, such as double or triple bonds. But before we start looking at how this is explained, we are going to do a quick little recap and review of what we learned yesterday. So yesterday we took a look at how bonding between atoms takes place between unpaired electrons that are found in the various orbitals. So the first one that we took a look at were between half-filled s orbitals, as in the case of two hydrogen atoms. The two half-filled hydrogen atom orbitals will overlap and form the covalent bonds, allowing for it to have two electrons being shared between the two orbitals. The next case that you can also have involved p orbitals. So a lot of different variations here as well. You can have an s and a p orbital that are half full, and where they will overlap and form a covalent bond. Or you can also have two p orbitals which are half full, such as in chlorine molecule of Cl2, F2, Br2, and so forth. Each of those have half-filled p orbitals where they overlap and form a covalent bond. The last thing that we introduced is how hybrid orbitals also can have the overlap of these orbitals with other s or p orbitals of neighboring atoms to form a covalent bond. And we learned about three different hybrid orbitals. First one being the sp orbital, which we saw in beryllium atoms due to the promotion of one electron into an empty p orbital. This is a linear structure, and this sp hybrid is able to form a maximum of two covalent bonds. We also looked at the sp2 hybrid, such as the case of a boron atom. Once again, an electron is promoted from an s orbital to an empty p, and so it results in having one electron in an s and two p orbitals. This particular sp2 hybrid orbital has a trigonal planar shape. And the last one we saw yesterday was the sp3 hybrid orbitals. These are formed in atoms such as carbon, which allows it to form four covalent bonds. And as in the previous two, one of the electrons from the s orbital gets promoted to an empty p orbital, and that is how we have this sp3 hybrid orbital that forms a tetrahedral shape. These orbitals all directly overlap with one another and form our covalent bond. Now this direct overlap, yesterday we did not name it, but today we're going to give it a name. This particular orbital are all called sigma bonds. When we have two s orbitals overlapping, as in my first case here, so this overlap, this here is called a sigma bond. The overlap of two p orbitals is also called a sigma bond. And the overlap of an s orbital of hydrogen and an sp3 orbital of, say, carbon is also considered a sigma bond. Okay, so these are all examples of sigma bonds, where we have the direct overlap between s and p orbitals and hybrid orbitals. Now, these sigma bonds that we have just studied do not explain multiple bonds and how those are formed. So a different type of bond must exist in order for molecules to be able to form double and triple bonds. And so we're going to learn about those today. When we see this type of bond formation needed, you are going to see parallel overlap that results in the formation of a new type of bond. And the name of this bond is a pi bond. And so what we're going to see in the next few examples is that regular unhybridized p orbitals found between the two molecules that may form double or triple bonds are going to overlap sideways and not end to end. And so this is going to produce an electron density region in two separate parts. One that's going to lie above the plane and one that's going to lie below the plane. And so to make up a pi bond, it requires both of these regions found on this imaginary line between the two atoms. This we call a pi bond. So let's take a look at some examples of this and what we mean by this. So there's always going to be two parts to a pi bond, and both are always going to be necessary. So here's a visual diagram to show you exactly what this is. When we have two p orbitals overlap side by side, we see the overlap. There's two overlaps here. Okay, they're overlapping in both regions. This is where the electron can be found in a pi bond. So these two regions here and here, these are the two areas in which the electron pair can be found. So they can be found in the upper electron density cloud, or they can also be found in the lower electron density cloud. So first one that we're going to look at now is how are double bonds formed. Okay, so this is the first one that we're going to look at. So the example we're going to use is carbon, because carbon is one of those unique atoms that can form single bonds, double bonds, and triple bonds. So let's see how carbon is able to form a double bond. If we recall, this row here represents carbon's valence orbitals. Okay, this represents carbon's valence orbitals. Okay, and so as we see, this electron is promoted to the empty p orbital. So instead of, when we have to form 4 single covalent bonds, we form a sp3 hybrid. Instead, what happens is there's a partial hybridization. And what ends up forming instead is that one s and 2 of the p's hybridize to form an sp2 hybrid, leaving an electron in a normal or unhybridized p orbital. All right, and so that is what's going to allow for the formation of our pi bonds. Okay, so very, very important that we call this partial hybridization. Okay, partial hybridization has to happen when we've got to form a double or triple bond. All right, so in our example, instead of mixing all 4 orbitals, what the valence bond theory suggests is that only 3 are used to blend or hybridize to form an sp2 hybrid orbitals, leaving an unhybridized regular p orbital which contains a unpaired electron. So this is very, very important. So now we can take a look at this visual diagram here of what actually is happening. If we look at here in the blue, these 3 are our sp3 hybrids, sp2, sorry, they're sp2 orbitals. In each one of them, there is an unpaired electron, which can be involved in bonding. As well, in perpendicular to the plane, is this unhybridized regular p orbital, which also contains a half filled orbital with one electron. And so it is going to be used to form our pi bond. All right, so it's very important to realize that sp2 hybrid orbitals are trigonal planar. They have a trigonal planar shape, lying all in one plane. As shown in this diagram. And perpendicular to it is the unhybridized normal p orbital. So I'll put that over here so you realize that perpendicular to it is the unhybridized p orbital. All right, so now let's take a look at an example. Ethene is a good example to look at, which contains a double bond. So there's two things that have to occur. The first step, so this is step number 1, a sigma bond needs to be formed between the sp2 hybridized orbitals on the carbon with the s orbitals of hydrogen. Okay, so this is going to happen to two of them, and they're going to have regular overlapping. All right, so what you see here in this diagram is the formation of the sigma bonds. I've got a sigma bond here. There's one sigma bond being formed, which is my overlap right here. I got another sigma bond overlap, another one on this side of the trigonal planar, so this is also a sigma bond, and over here is a sigma bond. As well, between the two carbons is another overlap, and this too is a sigma bond. All right, so we have 5 sigma bonds that take place between the carbon and the hydrogen. So in electrons, I'm going to have 2 electrons being shared here, 2 here, 2 here, 2 here, and 2 here. All right, they're going to overlap end to end. Now, what you got to imagine that perpendicular to the 2 carbon atoms is the normal p orbitals. And that's what forms my pi bonds. Okay, that is what's going to form the pi bond. These unhybridized p orbitals on each of the carbons. So that's step 2. So this here in the yellow represents the sigma bonds that have formed between the 2 carbon atoms as well as the hydrogen atoms. And so what's sticking out above and below the plane are the normal p orbitals. Okay, and so what happens is this is my electron density cloud, and this one here is also my electron density cloud, and it forms a pi bond. All right, so that's going to result in the formation of our pi bond. Okay, so it's going to form, if you take a look at this next diagram, it shows the 3-dimensional electron clouds that form above and below the sigma bond. So I've got 1, 2, 3, 4, 5 sigma bonds, and then my pi bonds is always 2 electron density clouds above and below that initial sigma bond between the 2 carbon atoms. So for ethene, there are 5 sigma bonds and 1 pi bond. Okay, and the pi bond is between the 2 carbon atoms. All right, now we're going to take a look at triple bonds. What happens in the case of the formation of a triple bond? We know that when we built our triple bond molecules like ethine, we knew that this was a linear molecule. And so the reason that it is linear is because of the partial hybridization that forms once again. So in the diagram here, once again for carbon, we're going to use carbon because carbon can also form triple bonds. We see that once again the electron is promoted. The electron is promoted. Whoops, don't know what's going on there. The electron is promoted to that empty p orbital. And so instead of doing a full hybridization, which would happen in the formation of 4 single bonds, what happens is a partial hybridization between 1s and 1p, and thus it forms an sp hybrid. And if you recall from yesterday, sp hybrids are linear, and it leaves us with 2 normal unhybridized p orbitals, one along the y plane and one along the z. Each of these normal p orbitals contains 1 electron, able to form an additional pi bond. All right, so this shows the 3-dimensional diagram of what it looks like. This one here of carbon is got 1 electron. This sp hybrid also has an electron, so this is called an sp hybrid. And this side is also called an sp hybrid. As well, I've got one along the y plane that has 1 electron. That's my normal p. And there's another one along the z plane that also contains an electron, which is found along the z plane. All right, so each of those normal p orbitals, these are called, we call them different things. They're called normal p orbitals or unhybridized p orbitals. So let's take a look at our example. So here again is an explanation of what's actually taking place. With respect to carbon here, it partially hybridizes so that it results in 2 sp hybrid orbitals and 2 unhybridized p orbitals. And so it's going to produce our linear molecule that allows for the overlaps to form. So step 1, when we think of the molecule ethine, what needs to happen is the sigma bonds must form between the 2 carbon atoms first. All right, and so that's what's going to happen in this case. Okay, there's going to be an overlap here. All right, so this is going to form my sigma bond between here. There's going to be a sigma bond over here and another sigma bond here. All right, so there's going to be 2 sigma bonds between this carbon here and the hydrogen. There's a sigma bond between the sp hybrid and the s orbital of hydrogen, and likewise on the other side. Okay, and so what ends up happening is the pi bonds form above and below the initial sigma bond. And so what we have here is the following. This one here and this one forms 1 pi bond. And then we have this one and this one forming our second pi bond. Okay, so what ends up forming in this particular case of ethine, which is C2H2, it has 3 sigma bonds and 2 pi bonds, which results in the formation of a triple bond. So you've got that red bond represents 2 electrons, another pair of electrons along the black, and a third pair of electrons along the green. Here's another illustration to show where those sigma and pi bonds are found. Okay, so we've got 1 sigma bond, 2 sigma bonds between the S. So you're going to have it between carbons sp hybrid, orbital, and hydrogen's s orbital. And that happens on both ends. And there's also the 2 sp, so these are my sigma bonds that forms. So it's between the carbons sp hybrid and hydrogens s orbitals, and the second one is between 2 sp orbitals of the carbon atoms. And that's how we get the 3. One sigma bond, a second S sigma bond, and a third sigma bond. And then above and below it, we have a set of 2 pi bonds. All right, 1 pi bond, 2 pi bonds. So in order for a triple bond, whenever we're going to form a triple bond, it will always entail 1 sigma bond and 2 pi bonds. So that initial sigma bond has to first form between the 2 carbon atoms. Once that occurs, the unhybridized p orbitals will fall into place and form our 2 pi bonds. All right, so hopefully that makes sense. It is really, really important that over the next couple days, folks, that you read over section 4.6, and it's very imperative that you try the homework questions on page 238, numbers 2 to 8. If you have any issues, please make sure you ask in the discussion section in the toolbox on the LMS page. All right, good luck, have fun, and we'll talk to you soon.